2 dB or not 2 dB? That's the question. And of course, we're talking about full matrix capture, total focusing method, and amplitude fidelity, and how the core digitization principles that we've discussed in previous episodes are applicable here. This will be the 7th and I think final installment of my Digital Revolution video series. This time we're going to talk about TFM, grid resolution, pixel size, and amplitude fidelity. If you missed episodes 1 through 6, check those out first as this discussion builds upon those. Those topics are listed here on this page, and I'll leave a link up here at the top. And when you're all caught up, meet me back here so we can level up those UT skills. For TFM and FMC, both ASME and ISO codes have a general amplitude fidelity requirement of 2 dB or less. Both codes describe how that is achieved, or maybe not, based on the density of the TFM grid resolution, and both codes give suggestions on ways in which this can be verified. A little bit more on that later. So how do we get there? Well, that's why we're here. If you remember in the 3rd video of this series, we discussed timing fidelity and error, which basically means how close a digital sample lands relative to the location of the analog peak at a given worst case scenario. This parameter is related to our time of flight measurement accuracy, as well as the preservation of the frequency information of our signal. And in the 4th video, we considered amplitude fidelity, how closely the amplitude of the digital waveform represents that of the original analog at the same worst case scenario. And then we also simply define fidelity, the degree of exactness with which something is copied or reproduced. So in all those discussions, what it really boils down to is this: how closely does our digital waveform represent the original analog, both in terms of time or position and amplitude? In each of those lessons, we calculated several scenarios for each version of fidelity, so be sure to catch up on those for more information. That's all going to be important information and principles to understand moving forward. The FMC and TFM technique can be broken down into 2 sets of steps. So part 1, data acquisition, and part 2 is going to be data or image processing. So first, let's talk about step 1. We're going to collect raw ultrasonic waveform data. Full matrix capture is the classic data collection strategy, but it's not the only one. You have half matrix capture, sparse matrix capture, and plane wave imaging. Those are other viable options that are common in the industry, and there's also some that are a little bit less common. Regardless of which data collection strategy we choose, the result is similar. We get a collection of raw waveform data that we call elementary A scans. And in order to make sense of the data architecture of those stored elementary A scans, we typically present them in an XY matrix pattern that typically shows our emitters versus our receivers, and more on that soon. This is an animation published a few years ago by Olympus, now evident. It shows the classic FMC sequence: pulse with 1, receive with all. And then you're going to collect what we call elementary A scans, 1 for each receiving element. Each elementary A scan is digitally sampled, and each sample contains time and amplitude information. Pulse with 2, receive with all. Pulse with 3, receive with all. So on and so forth. You repeat the process until all the pulse and receive combinations have been acquired. The full matrix has now been captured, and the total number of elementary A scans equals n squared. The 3D image on the right shows the number of pulsing elements versus the number of receiving elements and the associated digitally sampled A scans, again, each sample containing time and amplitude information. Here's another way of looking at the matrix: pulse with 1, receive with all. Pulse with 2, receive with all. Pulse with 3, receive with all. So on and so forth until we pulse and receive with all of our possible element pairs. Now, obviously, in most cases, you're going to be collecting FMC data using a probe with a larger element quantity, like 32 or 64. But this is good enough to get the point across of the principles involved in data collection. The resulting display here shows the full matrix capture of elementary A scans that was collected from all of our pulsing versus receiving element combinations. The total number of elementary A scans for FMC can be calculated by the function n squared. For n number of pulsing elements, there are n number of receiving elements. So in this case, 6 times 6 would be 36 elementary A scans. If you had a 32 element probe, you would collect 1,024. And with a 64 element probe, you would collect 4,096 elementary A scans. Also, something that I saw misunderstood by some a few years ago, this FMC matrix is not to be confused with our TFM grid and the resulting pixels. That's something that we'll cover soon, but we have to understand that FMC data collection and TFM data processing are two completely separate functions. And like we said earlier, FMC is just one of several data acquisition strategies. You also have half matrix capture, sparse matrix capture, plane wave imaging, and some others that are possible. These are all basically variations of FMC, each with different benefits such as maybe file size or scanning speed or penetration improvements or some collection of those. To detail each one of those is beyond the scope of this presentation, but those are all topics that we cover here at our 80-hour FMC and TFM course at the University of Ultrasonics. So if you haven't come to see us for that, you are missing out on something that I'm quite proud of. In 2026, actually, we're going to be entering our 7th calendar year of holding that class, and it keeps getting better and better as the technique matures and develops. But regardless of which acquisition strategy we employ, the result is a matrix of elementary A scans that we will then apply TFM processing algorithms to in the next step. Each one of our collected analog elementary A scans within the matrix is then digitized and sampled along the time base at a regular interval, and that's going to be determined by the speed of the instrument's digitization frequency. Each sample point contains time and amplitude information, and the amplitude precision is largely controlled by the bit depth of our instrument. At this point in 2025, for the current generation of TFM capable phased array instruments, the typical digitization frequency is 100 megahertz, and the typical amplitude bit depth is 16 bits. And both of those topics were covered in detail in previous videos in this series. This is a real example of an FMC elementary A scan. So to begin with, they get recorded in RF. The constructive and destructive interaction that phased array historically would sum together using the pulsing and receiving delay law patterns will instead be calculated, then delayed, and then summed by the TFM algorithm in the next step. Phase information, and by that I mean the positive and negative displacements and their resulting amplitudes, those have to be preserved so constructive and destructive interaction can be calculated by TFM. These elementary A scans are typically very low amplitude and show very long time bases. Theoretically, every ultrasonic interaction that was possible with a given probe and wedge on a given part, including reflections, refractions, mode conversions, skips, that sort of stuff, those are all hidden away somewhere in the samples across the A scans in the matrix. It's very hard for us to decipher this ourselves. That's why we employ the advanced TFM algorithms to do that for us. This is another example of a way to display FMC data. This was put together in MATLAB. All the elementary A scans for a 32 element probe are shown here. Any guesses as to what this all means? The red box shows element 1 firing. Receiving is shown from elements 1 through 32, left to right within that red box. I've got a zoomed in image there of the first 4 elements pulsing, and receiving is going to be with all 32. This red box shows the last element pulsing, and again, receiving is with all elements. Now the red box shows the probe pulsing and the associated wedge noise. And then these are the signals in the part that are used to construct the TFM image. And this is the resulting TFM image after the delay and sum process. Of course, to get this image right, our TFM variables have to be properly set when we get to that step. That's kind of above most of the scope of this video. We'll talk about some of it, but for now, let's continue with FMC elementary A-scan quality. If you remember in previous videos, I showed you how to calculate sampling rate based on your probe frequency versus your digitizing frequency. I showed you how to calculate this in a few different ways, but I'm just using the simple version here. Your digitization frequency divided by probe frequency equals your sample rate. And the scenario we're looking at here involves us achieving 5 digital samples per period. So what sort of digital quality or fidelity would this result in? First, for timing fidelity, and remember, There's a distinct difference between timing and amplitude fidelities, as I've already explained. For this scenario, we're going to consider using a 5 megahertz probe and a 25 megahertz digitization frequency, resulting in 5 samples per period that would be equally spaced along the cycle. This is often called ideal minimum sampling. So notice in this scenario, none of the samples aligned perfectly with the peaks, but the second and fourth samples got pretty close. And shown here are some simple calculations I showed you how to do in previous installments. This is representative of a worst case scenario when digitizing an analog signal, when the peak is centered between 2 samples and we lose all the timing and amplitude information of the peak. Basically, everything above that blue line is lost. And since we're dividing the period by 5, the interval between samples represents about 20% of the cycle. If you divide that again by 2, you'll see how close in percentage the sample is to the timing or the location of the peak. In this case, we're within 10% of the location of the peak. So 10% timing error, 90% timing accuracy or fidelity, somewhere in that ballpark. You'll often hear that 5 samples per period keeps you within 10% of the original analog waveform. Well, that's true regarding timing fidelity. Worst case scenario, it ensures that no sample is any greater than 10% away from the location of the peak. But that's not true regarding amplitude fidelity, and we'll recap that in just a second. Same scenario as before, but now I'm using a real-world example. A 5 megahertz probe, just doing an L-wave exam on carbon steel, and the associated velocities are there on the page. 10% timing error would equal about 0.004 thousandths or 0.12 millimeters, as we calculated in previous lessons. In video 4, we calculated amplitude fidelity, so same scenario, 25 megahertz digitizing frequency, 5 megahertz probe, 5 samples per period. The worst case scenario is shown here. The peak is perfectly centered between 2 samples. If you work out the phase spread, we'll find that there's 72 degrees between samples. We can convert that to our maximum phase error and show that there's 36 degrees between the samples and the peak. If you convert that to a percentage, you'll get within 81% accuracy and have maybe about 19% error, give or take. And if we convert that to a dB, we can show that we're within 2 dBs of amplitude error. 5 times your probe frequency, which gives us 5 samples per period, aka ideal minimum sampling, is said to keep us within 2 dB of the amplitude of the original signal. And here's the mathematical verification of that. Most of the TFM capable phased array instruments on the market today use a fixed or standard digitization frequency of 100 megahertz. So that would be 20 times the frequency of a 5 meg probe, resulting in a sampling rate of 20 samples per period. And you could calculate this for other scenarios. We did that previously. Here's a representation of what that would give us with a 5 megahertz example. Sample spacing is much tighter. This time, the interval between samples is now about 5% of the period. I showed you how to consider a worst case scenario for digital sample placement versus the original analog peak, and we use that to calculate timing error and timing accuracy, also known as fidelity. For this example, the timing accuracy is preserved to about 97.5% or better, limiting our error to about 2.5% or less. We also applied that to real-world situations. In this case, the 5 meg probe, L-wave on carbon steel, and we calculated a potential time of flight error in inches and millimeters. As you can see here, more samples per period, which results in a smaller margin of error between samples, gives us outstanding timing accuracy or fidelity, which will be imperative for FMC and then later TFM. In video 4, I showed you how to calculate amplitude error and fidelity in the same scenario. These calculations will also be looked at when we get to our TFM grid parameters. It's kind of related, a little different. In this case, our amplitude error is about 0.1 dB. So as you can see, when we record our elementary A scans with 100 megahertz digitizing frequency, we're able to capture very high resolution raw A scans that have very good fidelity when compared to the original analog signal. That's how we do it for FMC and our other data collection strategies. So before we move on to the TFM discussion, first, let's think about how standard phased array focuses. We know from first principles that focusing is limited to the near field of the probe, and we could have an entire series of videos dedicated to the near field. We probably will, actually. It gets really complicated, especially when you get away from round crystal transducers and start considering square and rectangular apertures that we use for phased array. Honestly, I spend a lot of time in my classes covering this stuff to the point of exhaustion, and we don't have the time for that right now. But the limit is the near field for true focusing. Beyond the near field of the aperture, phased array and conventional UT cannot achieve a true focus, and even TFM cannot synthetically calculate a true focus. The things that drive the near field are numerous, but frequency, aperture size, velocity, your wedge, and refracted angles, others, those all play a role. In addition to focusing being limited to the near field, it's also based on the steering capabilities of your probe, the element size, the wedge properties, and angles. If phased array cannot properly steer a beam to an extreme angle, you obviously would not be able to focus there either. And phased array focusing is limited to one plane at any given time. So you've got true depth, sound path, half path, projection. Those are all focusing geometries that we can use with phased array. And they're performed by shaping the focal law as we emit the beam. If we're focused at 1-inch depth, we cannot also be focused at 2-inch depth at the same time. If we're focused in true depth, you can't simultaneously focus in projection. Different focusing paths and focusing types would all require multiple pulses of the probe. So on this example here, I've got about 200 grid points for these examples. I had the grid pattern set to about 2 millimeters. If I wanted to focus at each point, it would require 200 individual pulses, which would obviously take some time. On this one, on the left example, I changed the grid resolution to 1 millimeter or 40 thousandths of an inch. Now you've got about 800 grid points. So that would be 800 pulses with phased array. That's going to take a long time, right? In TFM, just like phased array, our resolution actually needs to be a fraction of a wavelength. So on this right example, I changed the grid resolution to 0.005 or about 0.12 millimeters. That would be about 43,000 grid points, which would require about 43,500 pulses with phased array. That's obviously going to take forever, and we're not going to be able to do that. Each individual sound beam created within the scan has to go through the pulse and receive cycle as shown here. You should remember something like this from your phased array class. And there's a time delay calculated by the focal law for pulsing and receiving with each individual element being used. An example of that is down there on the bottom. Only one beam can be pulsed at a time, and it has to be received before the next one can fire. So focusing everywhere with phased array and maintaining a high image resolution, like a fraction of a wavelength, it's just not going to be possible. It would take forever. TFM, on the other hand, calculates all these same pulsing and receiving patterns and applies synthetic algorithm delays in post-processing. Each focal law that phased array would have used to focus at each point, TFM can calculate those same patterns and apply a delay in sum process on those raw elementary A scans, effectively focusing at every point within a high resolution grid. There are some hard limits to TFM focusing, just like phased array. If phased array could focus at a location by shaping a certain focal law, TFM can calculate it with the algorithm. If phased array could not achieve a focused focal law at a region, TFM will not be able to calculate it there either. The near field of the entire aperture, as well as the steering capability of the individual elements, still going to be a limiting factor. We obviously don't have enough time here to cover everything. We're on a kind of a specific mission at the moment. All of those things are covered in detail in our class. Okay, now that we've completed step 1, the acquisition of elementary A scans, step 2 is data processing. And that's where your TFM algorithms come into play. Total focusing method, TFM, that's the classic data reconstruction technique. It's widely considered to be the gold standard in both medical and industrial imaging. There are others such as phase coherence imaging, adaptive, and other ones. Those are topics for another day. Regardless of the data reconstruction technique we choose, the following processes are similar. First, we must identify a region of interest within our part. That's sometimes often called a frame or a zone. Once we've identified a region of interest, a grid is then meshed within it. So to me, this is kind of similar to what you would see on a high definition TV. When you stand too close, you can see the grid pattern and the pixels on the screen. Or even like the grid pattern you see on a standard window that we use to keep bugs and other critters from getting in the house, our window screen. The TFM grid spacing is at the heart of our discussion today. Too coarse of a grid, and we chance missing small discontinuities, or even having too little resolution to maintain the desired fidelity of the signals that we do find. Too fine of a grid pattern will give us excellent detectability and resolution and fidelity, but then we risk unproductive scanning speeds and file sizes. So, like in all UT testing, we sort of have to strike a balance between data quality and data quantity. There are also a lot of other factors to consider after we set the grid. So your wave mode and velocity, the image path or wave set that we use to position the data, etc. There's a lot of things. And again, beyond the scope of the current discussion, but those are all covered here at our 80-hour class at the University of Ultrasonics. One of the first items we have to consider, again, when setting our TFM parameters is the size and position of our frame. Typically, it'll be square or rectangular shape and defined by 3 parameters. So you've got the length or width along the x-axis, you've got the height along the y-axis, and then the general location within the part. Think about this like a picture frame or a window frame. It defines the perimeter of your area of interest relative to your probe, and it will define where TFM will calculate. So here's an example of setting the frame within our area of interest. What I'm showing here is an extended TT setup on a single V weld, and my frame is set to capture the area of interest in both the first and second legs. Here you can see the first and second legs, some weld geometry, and a nice lack of fusion indication on the bevel. This is called a TFM end view. This is what TFM actually creates. It's a 2-dimensional frame or region of interest with a grid meshed within. And the end view shows the ultrasonic or depth axis versus the index axis. I'm showing 2 scenarios here, a high resolution grid versus a low resolution grid. For the fine grid, we have better image quality, resolution, and fidelity, but more and better data also comes at a cost, slower scanning speeds and a bigger file size. The coarse grid on the right has poor resolution and fidelity, but since we're collecting less data, the scanning speed would be faster and the file size smaller. Of course, amplitude fidelity is the hot term that everybody throws around, but you have to also understand, on a coarse grid, you'll also have timing or positional error, which means our non-amplitude measurements like depth or through-wall height could also be jeopardized if the grid resolution is too coarse. Every grid point is a source of information. Your pixels are going to be centered and overlaid on top of each grid point. The maximum summed amplitude at the grid crossing point equals your pixel color intensity. And depending on screen display resolution, there may be multiple pixels, all the same color, the same amplitude intensity for each grid point. So the term pixel can actually be a little misleading. Think about a low resolution monitor versus a high resolution monitor, or what actually happens when you zoom into an indication. And you can kind of think of it like this. Would you rather watch your favorite sports team on a TV with a 480p screen resolution or a 1080p or a 4K screen? It's a similar concept. A tighter grid spacing equals more pixels in the area of interest, which then equates to better signal resolution. Many of us attended the AS&T conference in Vegas in 2024. Remember the Sphere? Massive screens, super high resolution. That one was using a 16K digital LED display. So what does that even mean? Well, if your region of interest or zone or frame or whatever you want to call it, if that needs to be bigger, if you increase it without increasing the number of grid points or pixels within it, your grid point to grid point resolution will suffer. Larger regions of interest require more grid points to maintain the same grid density, resolution, and fidelity qualities. Both ASME and ISO give suggestions for ways to improve the 2 dB amplitude fidelity. And also the grid point to grid point spacing is largely said to be related to lambda divided by 5, kind of like our ideal minimum sampling, to meet that 2 dB requirement. See the code sections I listed above for more details, but basically both suggest, not require, and that's an important distinction, different ways that you can physically perform a check. ASME mentions one version, scanning a probe with an encoder with a really tight resolution to scan across a side drilled hole and measure amplitude fluctuations as the grid moves across the hole. ISO goes a step further, and they actually suggest you hold the probe down and electronically move the grid across multiple holes located in different parts of the frame in order to do the check. basically in increments of wavelength divided by 20. So essentially 20 grid movements equal to lambda divided by 20. And they both describe either doing vertical grid movements or horizontal grid movements, or maybe both. This is sort of how that would look. So the left action, maybe that's like moving the probe horizontally and letting the grid move with you along the holes as you scan down the cow block. And the right action, that would be kind of like holding the probe still on the cow block and moving the grid electronically. And that motion could either be vertical or horizontal. Remember, the proposed grid spacing or resolution is currently lambda divided by 5 or smaller, and the holes or grids are moved in lambda divided by 20 increments, either left to right or top to bottom. Let's say that we've somehow managed to zoom into the center of 4 grid points within our frame, and our grid point to grid point spacing, aka resolution, is lambda divided by 5 in both the horizontal and vertical positions. That should meet the proposed spacing interval to have a grid point to grid point resolution of 5 points per wavelength, which should give us 2 dB or better amplitude fidelity, the same way ideal minimum sampling achieved that for point-to-point spacing between samples, as we discussed previously. Now let's think of it from a real-world perspective. 5 megahertz testing frequency, carbon steel, shear wave. We have our known wavelengths. If we divide that by 5, we get a grid point to grid point spacing of about 0.0051 or 0.13 millimeter. So according to the old assumption of lambda divided by 5, we should be good, right? Well, not exactly. There's a problem. Let's use easy numbers for a moment. Let's say the vertical spacing between grid points is 1, and the horizontal spacing is also 1, since we have a square grid pattern. And remember the Pythagorean theorem. A squared plus B squared equals C squared. And you could also write that as C equals the square root of A squared plus B squared. In this case, A and B are the vertical and horizontal legs between grid points, and C is the hypotenuse of the square of the triangle. If the legs are 1, then the hypotenuse is a little over 1.4. There's a 1.41 to 1 ratio between the legs and the hypotenuse. Why does this matter to us? Because in reality, the true orientation of a flaw is rarely perfectly vertical or horizontal, and we need to understand that during the FMC and other collection processes, just like phased array, we may be dealing with angular beam propagation and angular beam impingement on our flaws, so we actually need to consider the diagonal. Here's another way of looking at it. If we don't consider the diagonal and our grid is too coarse, it's possible that we may not find the true maximum of the original signal. So amplitude fidelity will be off, but also we lose accuracy of exactly where to measure the position of the signal because our timing fidelity is also off. Let's say the center of the red is the peak of the signal here on this example. If my intersecting grid lines don't see it, I cannot measure it accurately. Look at the color of each grid crossing point. That would be the amplitude intensity of the pixel placed there. And as you can see, none of them in this example found the max. So we need to consider the diagonal, and to do so requires a little more math. We now know that the hypotenuse is 1.4 times the legs, so let's multiply 0.005 by 1.4, and you can see that our hypotenuse is actually 0.0072 inches, or about 0.184 millimeters. If we divide our wavelength by that value, we'll see that even though we have lambda divided by 5 on the legs, we're only sitting at about lambda divided by 3.5 on the diagonal. So grid point to grid point spacing of only 3.5 points per wavelength as opposed to 5. Let's work out our amplitude fidelity exercise from video 4 to see what quality that would or probably would not give us along the diagonal. As we calculated in video 4, when point-to-point resolution is lambda divided by 5, we achieve at least 80% accuracy, limiting our error to less than 20% or 2 dB. And remember, this was our original thought process for TFM grid spacing requirements. Instead of sample point to sample point spacing, now it's grid point to grid point spacing, but the math and the basic concepts are the same. But like we said before, that would only leave us with 3.5 points per wavelength along the diagonal. So if we work that out as before, we could calculate that we would only have up to 63% accuracy, leaving us with up to 37% error potential, which would result in us possibly being 4 dB out on our amplitude fidelity on the diagonal, over twice the code stated allowable error, and twice the potential error calculated for the horizontal and vertical legs. And later on, we'll see if that double dB error on the diagonal holds up on a practical test. So here's the solution. Achieve lambda divided by 5 on the diagonal, which we know should give us 2 dB there. If you take that value here, 0.005 inches or 0.13 millimeters on this example, and divide it by 1.4, that'll actually give us lambda divided by 7.1 on the vertical and horizontal legs between grid points. And if you run the amplitude fidelity formula on lambda divided by 7.1, you can see that we would only calculate 0.9 dBs of error there. That would be well under our 2 dB requirement, and it would mathematically work no matter the orientation of the flaw or the propagation of our energy relative to the grid. So that may be the number we should consider adding for our actual resolution input on our software. Another thing to think about, every calculation that we've ran on this series has only considered the center frequency of the probe, but we know that our probes are actually capable of producing and receiving over a range of frequencies. So think about the bell curve that we're all familiar with. There is frequency content that is both higher and lower than that of the center frequency. We want that slightly higher frequency range of the bandwidth to also be preserved, so we may need to set our resolution even finer in many cases to meet fidelity. For example, on the OmniScan X3 and X4, the 2 dB amplitude fidelity value actually triggers when your grid resolution is about lambda divided by 8, and that's for envelope off. This actually considers the diagonal in the calculation. It actually considers 4 axes of grid directions as well as the frequency range found on your bell curve that we just discussed. And it's worth mentioning, if you turn on the TFM envelope, you can actually achieve 2 dB at around lambda divided by 4. The envelope is created by a process called a Hilbert transform, and it can actually maintain 2 dB at a lower grid resolution, which can in turn boost your scanning speeds. I was going to cover that in this presentation, but this is already going to run pretty long, so you just have to come see me for our 80-hour TFM class, and I'll tell you all about the envelope on the day that we cover all this stuff. So I do trust the math that we've discussed and the way that it's calculated on the OmniScan, for example. I've verified it 1,000,000 times since we began teaching this class back in 2020. We do it as part of the class, and it works. And the math is all well and good, but at the end of the day, what can I prove on a cow block? Some people may be more concerned with that. And that's where this little guy comes in. A few years ago, Edify added an automated grid verification to the Gecko, and I've always thought it was really good. Basically, you put the probe on a cow block with a stack of side drilled holes, and instead of you physically moving the probe like ASME mentions, or manually adjusting the grid like ISO mentions, which by the way, that's very long and tedious. I've done it, and I'll show you how that looks soon. But on this, the software electronically moves the grid over the holes for you. All you have to do is hold the probe still and press a few buttons. It's easy, it's fast, it's pretty good. You can choose either horizontal grid movements or vertical grid movements, and the software moves the grid along the holes in 20 movements equal to lambda divided by 20 each, or you could choose another value if you wanted to. My only issue is that this does not consider diagonal propagation, and if you've been paying attention, that will mathematically have an effect. And as I'll show you later, I can also prove it physically. I would absolutely love to see it implemented in someone's software pretty soon. Hint, hint. As a wise man once said, prove me wrong. A similar grid verification and amplitude fidelity check is on the OmniScan X4 software. What's great about it is that both the horizontal and vertical grid movements are calculated at the same time, as opposed to the previous example where you had to choose one versus the other, and maybe you choose the wrong one. So I like that here both are performed simultaneously. And you can see on the bottom there is a difference between the vertical and horizontal results. A limitation of this one is that you can only gate and verify one hole at a time. A nice future enhancement of this process would allow us to perform multiple holes at once. And again, this function does not consider the diagonal. So why isn't the diagonal included in these checks? Simple, because the codes don't address it. ASME, ISO, they don't consider that part, but I think they should look into it. We all know that our industry likes to just meet code requirements without going overboard, but we've already mathematically proven that at least it needs to be considered. Every instrument and software meets the 2 dB requirement slightly differently. And this is another issue I have with the industry. If I had one each of all the major TFM players out there, the OmniScan, the Gecko, the Topaz, the Veo, the Cypher, and I had all those in front of me, and we built an identical TFM setup on each, with the only difference being what grid resolution triggered the auto 2 dB calculation, you're going to have a different experience on each one. Different scanning speeds, file sizes, varying levels of productivity. There's no parity or consistency from software to software, and it would sure be nice if there was. Everyone agrees how to calculate wavelength or velocity or beam spread, all the common calculations, all over the world, every textbook. But so far, we have not agreed on how to do amplitude fidelity TFM, and I strongly feel like that needs to be addressed a little bit deeper in black and white in future updates to the codes. So should it be less than lambda divided by 5 or 6 or 7 or 8? There's a ton of variables. Every situation's different. I think having a physical or software-based check is a good thing, especially if everyone gets on the same page as to how it should be done. And there are a ton of variables that could affect everything that we've been talking about. Here's a few. As you get deeper into your beam spread, you actually find longer wavelengths and a lower frequency response. I don't know how well you can see that on the top picture, but the white box is away from the center of the beam and the wavelength tends to get a little bit longer out there. And with FMC, if you only pulse one element at a time, we generate a spherical wave that essentially has infinite beam spread. And we use that to our advantage when we do FMC and TFM. Also, different flaws may reflect different frequencies. The grain structure or grain noise will do this as well. And what you discover is that bigger reflectors tend to produce a slightly lower frequency. Smaller reflectors like crack tips and grain structure, sometimes they reflect higher frequencies. And then the frequencies we get back to our probe are usually a little bit lower than what is nominal for that probe, especially in longer testing sound paths. The higher frequencies tend to attenuate more rapidly and your bell curve will gradually shift to the left. And then different cow blocks, materials, diameters of holes. Don't even get me started on temperature variations and how that affects velocities. It's a big deal. We talk about those things in class. Huge sources of error. So we have things that could affect velocity and frequency, so your wavelengths could vary, your points per wavelengths could vary. You get where I'm going? It might lead you to trust more on what you can see on a cow block versus what the math will tell you. And even, some of your high-end processing software like SIVA and BeamTool, I love both of those. But at the end of the day, what can you prove with a probe on a cow block? So to finish, I want to show you a little test that I did a while back, a few of them actually. I calculated diagonal grid movements on a spreadsheet, and then I manually entered those 20 diagonal grid movements, each one at lambda divided by 20. I used an oil-based couplant, so my couplant wouldn't evaporate and I wouldn't have sensitivity changes, and I strapped my probe to a cow block so it wouldn't move. This was very tedious. It took about 30 minutes per test to enter new numbers, wait for the instrument to process, and then take screenshots. It was actually a pain in the butt. But the results are at the bottom of the page. On the high resolution grid test at lambda divided by 8, which is what's required to get the 2 dB reading on the Omni, I only had 0.9 dBs of variance across all the grid movements. But on the lower resolution version, lambda divided by 5, I saw 2.2 dBs of variance. Not the 4 dB of potential error that we calculated earlier, but definitely not meeting the 2 dB threshold. Who knows, if I had scanned these horizontally, I probably would have been within 2 dB on both. And what you'll see, I was only monitoring one hole in the middle of the screen in the best part of the sound field. Kind of hard to say how much worse it would have gotten if the hole was somewhere else. I did both of these tests over a year ago before I had my X4, and obviously before the automated grid verification was in the software. So following each example, I'll actually show you how the OmniScan X4 grid verification performs on the same target now that I have that capability. And here are the screenshots of that test. Starting out, you can see the grid resolution, aka pixel size, was about lambda divided by 8, which is what triggers the 2 dB amplitude fidelity reading on the OmniScan like I described earlier. And the envelope was turned off, letting us see the signal oscillations provided by the raw elementary A scans. The AIM model on the top right shows the TFM frame position in the white box and where it's located within the acoustic field. And as I animate the slide, you'll see 20 grid movements along the diagonal at an interval of lambda divided by 20 between each one. And I'm looking at the gated signal of that bottom hole and the resulting amplitude measurement. The maximum recorded amplitude was 80.8 and the minimum was 72.4, which represents 0.9 dBs of variance, meaning this example would be compliant to both ASME and ISO codes. Here I've isolated the maximum and minimum from that example. The max is on top, the minimum's on the bottom. And you can see the top one showed a really sharp peak in the middle of the signal. And on the bottom, the peak is not as well defined, likely slipping between grid points. But because the grid spacing or resolution was so tight, the amplitude was still preserved within 2 dBs. Okay, as a quick supplement to the slides that I just showed you where I moved the grid along the diagonal on the high resolution example, I did that on my X3 about 1.5 years ago, before I had the X4 and before I had the automated grid verification. So we already know what the diagonal would give us, what sort of error. So we're going to check out this now on the new grid verification. Okay, now that we're on the grid verification screen, as you can see, I've got that signal gated here to sort of isolate where I want to calculate. Remember, this is one hole at a time, so I've isolated it with my gates in both depth and index positions, and I'm just simply going to hit add point. Okay, so what it calculated was 0.47 dBs on the horizontal and about 0.56 dBs on the vertical. And if you remember on the diagonal on the previous slide, I calculated 0.9 dBs on the diagonal. So you can see the diagonal is roughly half the quality of the horizontal and the vertical, which is what we've been sort of calculating earlier. On this example, the grid resolution, aka pixel size, was about lambda divided by 5. And you can see that's not sufficient to trigger the 2 dB amplitude fidelity reading on the OmniScan. And again, the envelope was turned off, letting us see the signal oscillations provided by the RF elementary A scans. Before we even start, you can see how obviously this signal does not have as good of a resolution of the previous one. Again, as I animate the slide here, you'll see 20 movements along the diagonal, each one at lambda divided by 20 each. The bottom hole is the one we're looking at, and we're looking at the amplitude reading. The maximum recorded amplitude was 82%, and the minimum was 63.8%, which represents a 2.2 dB variance, meaning this sample would not be compliant to either ASME or ISO requirements. And here I've isolated the maximum and min from that example. The max is on top, the minimum's on the bottom. You can see the top one showed a really sharp peak in the middle of the signal, but on the bottom, the peak is not as well defined. It's basically flat topped. This is a perfect example of what happens when the true peak is located between grid points on our TFM image. And since the grid spacing was coarse, we are out of tolerance for the 2 dB requirement. And like I mentioned earlier, this test was only performed on one hole and one position right in the middle of the sweet spot of our energy. So what would have happened elsewhere is hard to predict. Okay, and now what I'm going to do is change the resolution to 0.13 millimeters, which should give me about lambda divided by 5. And we're going to check out the lower resolution version. Now, notice real quick when I did that, the resolution obviously of the signals changed. Notice how the maximum amplitude dropped. It went from 80 to 77. You're going to start losing amplitude fidelity of your signals at a lower grid resolution. And what we're going to do is go to the grid verification. And again, I'm just going to adjust these gates down here to make sure I'm basically isolating on this bottom hole. Somewhere around right there, right? And I'm going to hit add point. And I'm reading 0.99 dBs of variance on the horizontal and 1.2 dBs on the vertical. And if you remember, we just calculated 2.2 dBs. This is for the lambda divided by 5 version. So again, the quality of the diagonal is about half the quality of what we've got here. We're around lambda divided by 1 for the horizontal and vertical. I was at lambda divided by 2.2 for the diagonal. There is absolutely a difference over that diagonal. And this is proof on the cow block, and you can correlate that back to proof with the math, and the diagonal needs to be considered. Okay, I think that'll wrap it up for today. As you can see, there are many variables that go into our assumptions of amplitude fidelity, how to calculate it, and how to prove it. And while our entire industry is concerned with amplitude fidelity as the hot topic for TFM, timing fidelity gets overlooked because it sort of takes a back seat. And that's unfortunate because our non-amplitude measurements like depth and through-wall height, those sort of get overshadowed and could potentially be jeopardized with the wrong approach. And what do I mean by that? Well, think about fracture mechanics. Not everything is based on amplitude. And also, if you only think about fidelity in terms of horizontal or vertical grid spacing, and you don't consider the diagonal, I believe that could get us in trouble too. Whether or not the codes ever take this into consideration, who knows? But I strongly feel they should at least look at it. It can be proven both mathematically and ultrasonically, as I've done my best to demonstrate here, that there is a potential for more error than meets the eye. And if the codes ever expand on this, I think it could set up more parity, repeatability, and consistency across our industry, regardless of what instrument or software is used. So anyway, I hope this digitizing series has been beneficial to the industry, especially the technicians out in the field who are largely in the dark when it comes to all this stuff. I know it's been a long haul if you've made it through all these videos. Trust me, it's taken me a few years to get it finished, but I did learn a lot in the process of building this series, and I hope it's been helpful. If it has, please like, subscribe, and share with anyone you think needs to see this. Take care, and I'll see you next time.